Yeah, hi, I'm Jerry Goldberg. I'm a postdoc here. I work on stars and supernovae. I'm one of the members of the MESA development team, and I also do kind of 1D and 3D simulations, and I'll talk about what I mean by that, and we'll, later.
And I'm Lieke, and so I'm also a postdoc here. I'm both in the Stars and Compact Object group and the Gravitational Wave group, which is both very big interests that I have. And we're going to be talking today about Stars and Co. And it's actually a pun already because it's stars and their company, but also stars and compact objects, because both of these are what we're really interested in and what we're trying to hope to get you enthused about. And we've engineered this talk to be really broad, to really get everybody on the same page. So we hope that in the end we've overcome our differences in fields and actually get to do some really interesting physics during the discussion session. So let me start about why should you care about massive stars at all? Well, massive stars are, they impact nearly every part of modern astrophysics. Their ionizing radiation is responsible for reionization epoch in the early universe. They are the chemical factories of our universe as they produce all the elements and metallicity that enriches our universe over time. They cause many of the most interesting transients that we see, not in the least the supernovae that at times can also be used as cosmological probes and ladders, which Jared will talk about a little bit later. Their late stages in particular are driven by particle physics and nuclear neutrino physics. And of course, they leave behind these very interesting compact objects that ultimately cause gravitational waves, or that we're now observing through gravitational wave detections. So really, to get everybody on the same page, what do we mean when we say massive star? Well, massive stars are these stars that are more than 10 times more massive than our sun. And as you probably know, we like to judge stars by their appearance. So we study stars by, since 1913, actually, people, both Hertzsprung and Russell, realized that if you sort stars by their color first, and then you sort them by their luminosity right after, is a little bit slower than I'd hoped, you get this really interesting pattern that is known as the Hertzsprung-Russell diagram. And it immediately already shows some really interesting facts about how stars live their lives, where they spend most of their time, and which stars are more common than others, which immediately shows these hot blue stars that are massive stars we're most interested in are a lot more rare than the low mass, less bright reddish stars. Where and how long stars spend their lives at different locations in the HR diagram is really primarily set by their mass. We catch most stars during their main sequence, obviously, because that's where they spend 90% of their lives, and they spend only 10% of less of their lives burning helium and successive nuclear burning phases. Now, this simple diagram was so effective that for the longest time, people thought, okay, well, stars are basically solved. They're kind of boring, we don't have to do anything anymore. But this image has gradually been changing around the turn of the millennium as more and more transient astronomy was growing, and we saw core collapse supernova, and people started to realize that we really do not understand the underlying physical properties that cause and set these observable surface properties that we see in this HR diagram. And namely, there is really a lot of different physics that goes into the evolution of a star. And I'm going to hand it off for...
Cool. So there's a lot of uncertain physics that goes into stars. Here's just sort of a smattering, right? So stars have hydrodynamics going on. There's interaction with the fluid in the stars. This manifests in things like shocks and convection. There's an equation of state that describes the response between the pressure, the density, and the temperature. There's energy transport going through the star via radiative diffusion via convection via other processes. There's nuclear reactions, which the rates are being constrained in labs on Earth, but then trying to extrapolate out to the objects and temperatures, densities present at the center of these stars. They have atmospheres. How do we model what that atmosphere looks like? There's neutrino physics and other kind of particle physics that maybe comes to bear on the stellar structure and therefore what we observe. There's also radiative processes, opacities, how the light interacts with the matter, both at the surface and in the deep interior. That's also relevant for energy transport. And there's potentially, magnetic fields, other phenomena. So really, there's a lot of physics here. And to make matters worse, we can't exactly just simulate this. So there are many scales involved if you want to, even before we go into massive stars, where radiation actually has to couple with the gas in both the energy and momentum equation. Even for the sun, even for a pure hydrodynamic model of the sun, if you want to actually resolve convection, you need to resolve from sort of the stellar radius scale global flows down to the viscous scale. This scale separation is about a few by 10 to the 7, which means to marginally resolve the sun, you need 10 to the 22-ish kind of fluid elements there. Well, what are the best machines we have? Moore's law says that the computational resources available for a given cost doubles every 18, about every 18 months. Right now, we're kind of sitting at 10 to the 10 or so we need about 11 orders of magnitude in computing before we can hold one snapshot of the sun. We extrapolate the Moore's law line, and we end up holding the sun on transistors in about 2070 something. Now, we can still make progress by simulating patches of stars or not resolving all of the convective scales, but this does place a fundamental limitation on exactly how much we can do just by this. So we'll talk later about how we get around this with different types of tools for different types of problems. So to shift gears a little bit, right, all this to say, stars are complicated. And to shift gears a little bit, like why are massive stars important, interesting? Lieke gave a lot of topics, but just to get us all on the same page, it's worth saying out loud, what is the life cycle of a massive star? Right, so we start with a cloud of gas. That cloud of gas contracts. Eventually, it gets hot and dense enough at the center to fuse hydrogen into helium. It then keeps going. It has a hydrogen-rich envelope, and a helium core builds up. That helium core eventually starts fusing into carbon, oxygen, nitrogen, all the way up to iron. At that point, it's only marginally energetically favorable to keep fusing beyond iron. That's not enough energy to power the star, so the iron core collapses under its own gravity. Somehow, and I'll mention how in one slide, often imparts enough energy into the rest of the envelope to actually explode the star. That leads to a type 2 supernova. I should also mention, when that core contracts, even as the helium core develops, it contracts, the envelope expands. This goes sort of the giant supergiant phase. So the star Betelgeuse in the shoulder of Orion is in this red supergiant phase. It becomes 1,000 times the radius of the sun, so it's like the sun goes out to the orbit of Jupiter or so, between Mars and Jupiter. Then it explodes. We see these explosions, we see that those stars, were there, then it gets even brighter, then they're gone. They leave behind black holes and neutron stars as these compact remnants, strew material throughout the universe. This recycling process happens, they form nebulae. Sometimes they don't explode. That is also interesting. And actually, for a long time, computer simulations could not explode stars. This was a big problem for a while. And the solution turned out to be a little bit boring, which is a more detailed description of neutrino physics and more resolution, more transistors, resolve the fluid scales. And again, these are going to be simulations just of the core of the star in 3D. I'm going to show a movie here. So the iron core forms and grows. It grows and grows and grows until it reaches the point when the degeneracy pressure and other thermal pressures in the core are not enough to support itself against gravity. That core then collapses. Right, so here's the star's core. It then collapses. The rest of the star is like, oh shit, there's no floor. Everything falls in, bounces off the core, and then that shock stalls because you can't drop a ball and have it bounce higher than you dropped it. Right? Same thing. So that shock is stalled. Simulations for a while couldn't pick that up. But then it turns out actually that neutrinos that get released when the protons and electrons combine into neutrons, and also maybe some flavor conversions matter, these then carry 100 to 1,000 times as much energy as you need to actually explode the star. And because it's so dense that the turbulence that's generated by these neutrinos streaming through, coupling just a tiny, tiny fraction of their energy to the stellar envelope, that actually becomes enough to aid in shock revival. Again, not always. This is, it turns out, dependent on just what is the density profile of that core, how much stuff is falling on your head. The shock revives, propagates. It takes only a second for the shock to start to revive, for this core collapse to happen, but it actually takes a day for that shock to travel at Mach 1,000 through this 1,000 solar radius star. So a day later, we see the bright flash of the explosion, and then we get a time-lapse view into the structure of the star, which I'll talk about in a bit. Right, and so when I say that this process is sensitive to the structure of the core and the neutrino coupling mechanism, this engine, what I mean is that different stellar evolution codes, such as Kepler, which is on the lower panels, and Franck, which is just another code on the upper panels, give you different results for which stars explode and which don't. So green here, we call them barcode diagrams. Green means the star exploded. Black means the star didn't. The initial mass is on the x-axis, and each one of these is a different efficiency parameter for the coupling between neutrinos and the matter. And people take 1.5 to be kind of a nice value, in part because it gives, roughly some fraction of stars explode or don't. But again, this is all based on stellar modeling assumptions, which differ between different treatments of that underlying uncertain physics. So, black hole formation, not a solved problem. We know most stars, or a lot of stars in this mass range explode. Not all of them explode, probably. That's also consistent with observed rates. And it's the core properties that determine that explosion, the energy, the nature of the remnant. But it's the properties of the star's envelope that determine what the star looks like and also the circumstellar environment. And so to understand emission from supernovae, we have to understand kind of both of these things, the structure of the core of the star and the structure of the envelope. And when I said time-lapse view, what I mean is you only see kind of an emitting surface, and as the supernova expands, you see deeper in. So at early times, you see the outer layers of the star, the environment, that's what determines the emission. Right? So the shock breaks out, you start to see a flash, you then see deeper in. The hydrogen-rich envelope then kind of causes this plateau. As hydrogen recombines, it gives this delayed release valve on the heat that just kind of radiates in this plateau. That sets the emission, but that's also dependent on the structure of that hydrogen-rich envelope. And then at late times, you see into the core, you see the geometry, you see the explosion geometry as well, where the nickel went out, the radioactive isotopes that then kind of heat the late time ejecta. And you can even see this is just a schematic of the luminosity versus time, that late time tail comes from the radioactive decay of nickel. That same radioactive decay is also what primarily powers the light curves of type 1a supernovae, which people use as cosmological probes. And this is sort of, my research focuses a lot on understanding, in particular, the envelope of the stars and how that imprints itself on explosions. So things that I like to think about are, how does the 3D nature of these giant convective, bubbly envelopes with convective cells that are of order the radius of the star imprint itself on early observables? So that's one thing that's kind of exciting, is that you can maybe use some of these observations coming up to probe what is that structure of the outer layers of the star. And another thing I'm interested in is, it turns out you can actually make a range of models that match observables in brightness and duration. So the upper panel is a light curve, luminosity versus time. The lower panel is the velocity you would infer from a spectral line, or or just by looking at the angular diameter growing of your emitting thing, right? What this means is you can see if you match the light curve, you basically get the velocities for free, except at the very early times, which are sensitive to all this, and the light curves don't agree either there. What this also means is that type 2p supernovae, these core collapse supernovae, they're called 2 because there's hydrogen, which is 2 instead of 1, then p because there's a plateau. These are standardizable candles. So this is kind of an independent probe of cosmology, can be, and people are thinking about this, an independent probe of cosmology that comes at a different delay time from star formation. They happen in different regions of the galaxy from type 1a supernovae, which are explosions of white dwarfs, which is what our sun will become only if it has a friend that donates material and then it explodes. The other thing is that these light curves, and these light curves are also shaped by things like mass loss and interaction with other stars. So this now is the same star where we've stripped away some of the envelope until it reaches different masses. We blow it up, we ask what does it look like? And the more mass you strip, the more the light curve kind of changes until you strip away basically all the hydrogen. And this also is important because as we're growing our understanding of stars and supernovae and all of this, we are also growing our understanding that most stars aren't alone.
Yeah, thank you. Yeah, this is actually particularly relevant indeed because since we now know kind of since 2012-ish, some people had some ideas before, but most stars live in binaries, and in particular, most massive stars, all massive stars, you could say, live in binary systems or more. So this plot shows, from a review from 2022, the fraction of stars that we expect to be in a binary system as a function of their mass, and you can see even at solar masses, already half of the stars live in a binary, but at high mass stars, all of them do. And this, even if you go to what is the higher order multiple fraction, so systems that live in triples or more, you can see that's the second line of crosses. We even expect like more than half of the massive stars to live in these higher order multiples. And so what it means for a binary to be a binary star is that it can interact with its companion. And these interactions, as the stars grow old and grow big, they start donating mass to their companions. This can do all kinds of things or induce all kinds of physics that we still don't understand. It can spin up the companion star. How much of the mass is contained by the companion star? Is it thrown off? How does the orbit change as the angular momentum is edited? Is this mass transfer, does it strip off the complete envelope of the donating star? All of these things basically give us a whole new picture of this binary evolution that adds a whole lot of questions along the ways on top of all the questions that we already had for single stellar evolution. So you could say this is kind of a lot of work, but it's also really exciting because, of course, there's a lot of new things that we can understand and a lot of new ways in which we can interpret transients as binary transients. And one of the important things in modern day binary physics is trying to understand whether that mass transfer that it's undergoing is really stable or unstable. And what we mean by that is that if the donor is donating a little bit of its mass, is its response such that it will lead to a runaway process, in which case we call it unstable mass transfer, and the star goes into what is called a common envelope situation, or is it not a runaway process and can it stably donate mass to its companion? And this is really crucial because this mass transfer dominates the change of angular momentum, and so it sets the final separation, the final fate, and the possibility of forming, for example, gravitational waves in the end. And so, although there's a lot of questions, this really is a very active field, and that makes sense because I would argue now is in particularly a really good time to be studying binaries. And that's because we are in the midst of what we would call a binary star renaissance. And Karim El-Badri put it really nicely, because in the era of gravitational waves, wide field surveys, and open source stellar models, binaries are coming back stronger than the 90s trend. And so through the rest of this talk, we're going to talk about these three elements that are shaping this binary star renaissance and how they are shaping the field as we are right now. So starting with my favorite, gravitational waves. I won't talk too long about this because we'll have a whole day on Wednesday. But we're now almost a decade since the first detection of gravitational waves, which was, of course, a merger of two stellar mass black holes, gravitational wave 150914, really being the starting gun of gravitational wave astronomy. Not much long after, we were blessed with the first binary neutron star merger, which showed us how really combining electromagnetic and gravitational waves can give us such a full picture of our universe. And it gave us new constraints in the equations of states of these systems. It constrained our process elements, so rapid neutron capture processes. And it showed that these neutron stars are the progenitors of GRBs. Since then, we've had a lot of detections since those first few detections, and this plot really shows how much faster gravitational waves are going with black hole detection, stellar mass black hole detection, and electromagnetic observations. So the yellow here is neutron stars, red is electromagnetically detected black holes, and this is the first catalog of binary black holes mergers, second catalog, and third catalog of gravitational wave mergers. And this summer, we are gonna see the first half or the first third, because there are now going to be 3 releases, of O4, which is already going to double the number of detections. So this shows number of detections as a function of time, and it beautifully shows how within a decade, we've gone from order of a few to order of tens to orders of hundreds of binary black hole detections. And this really is just the beginning, because we're now in the middle of O4, but if we project forward with next and third generation detectors, we're gonna get hundreds of thousands to millions of these detections. And so a lot of my work focuses on the question, how did they form? How do you form two binary black holes, or how do you get two compact objects so close together that they start emitting gravitational waves? Because gravity is quite a weak force, so you have to put stuff really close together before it makes any impact. Especially if you think about the massive progenitor stars that came before them, that are thousands of solar radii, where you have to have these binary black holes at orders of tens of solar radii. So how do you get those cores so close together is known as kind of the separation problem. And luckily, people have been very creative over the last many years, and there's been many, many formation channels proposed to overcome this separation problem. And very broadly, you can distribute them between isolated binary channels, which assume that binary stars are born together, and through their binary interactions, they change the angular momentum and get your compact objects close together. While on the other hand, you have dynamical formation channels that say, well, it doesn't really matter if your stars were born close together. The dynamical jumbling in dense environments like globular clusters or AGN disks can actually bring your compact objects to orbits close enough to get gravitational waves. And which of these four channels is dominant or responsible for the gravitational wave sources that we see is a really hot topic, because it also engulfs the potential to learn through these gravitational waves something about all of the uncertain physics that goes on in each of these different formation channels. And I want to plug a little bit the things that I do in particular. So this is a cartoon representation of the binary black, or of the gravitational wave mass function as it has been observed by LIGO, Virgo, Kagra so far. And very broadly, we have seen that there are features in this mass distribution. In particular, there are some neutron stars with some neutron star rays at the lowest masses. there's a global peak of the binary black hole mass distribution, and there's another peak detected at 35 solar masses. And I would argue that we now think, or we found, and other people also found this, that these neutron stars all form through this common envelope channel. They all have to go through this phase of unstable mass transfer, whereas the global peak of binary black holes could be a signature of stable mass transfer purely, and no common envelopes are needed. And there's a lot of questions still left out for this higher mass feature. But there is also a part 2 to this binary star renaissance, and this is happening still in electromagnetic light, because this shows over the next 20 years the landscape of the observational surveys that are going to be around. And we're expecting to see a lot of radio pulsars with SKA. We're going to be able to detect millions of supernova and transients with instruments like Rubin and SES5. And also Gaia is showing us a new way to astrometrically detect compact objects that really is complementary to these gravitational wave detections. So this plot is a really nice plot from Kareem again that shows these compact objects observed solely through electromagnetic observations, with the mass on the y-axis and the orbital period at which they've been detected on the x-axis. And these 3 black holes, Gaia, BH1, BH2, and BH3, have already proven that indeed you can detect stellar mass black holes in the Gaia catalog. And in mid-2026, Gaia is going to release their DR4, which will release all the data. And currently, there's still a cut on the Gaia data that limits specifically the detection of more massive systems. And so it's specifically biased against detecting these kinds of systems, or these kinds of more massive stars and more massive black holes. And so there's been a prediction that we might even see hundreds of these new types of black holes with Gaia. Similarly, they've also been detecting already 20 Gaia neutron stars. And so what's interesting is that you can start to ask questions of, are the populations of stellar black holes that we see through gravitational waves and the population of stellar black holes that we see through EM observations the same source population? Can we understand the stellar core to remnant mass function based on these very different observations? And already, one of the biggest questions that people have been thinking about over the last 20 years is there a gap between the most massive neutron star and the least massive black hole that you can form? And this has always been based on obviously electromagnetic observations, because that originally came from X-ray binary observations, which is shown here in this gray band. But if I now overplot the gravitational wave detections on random orbits, obviously, because they don't have a separation, you see that already with this gravitational wave population, this becomes a much vaguer answer. Even if you take out this one specific, I think there was a most recent detection that was very clearly in the gap, where everyone was clear, okay, this system is in the gap. But even without that system, the rate of black holes, mergers with black holes in this regime between 2 and 4 solar masses is not completely empty if you ask gravitational waves. And so this is an unanswered question. Is there really a gap between these two? Is there a discrepancy between these two populations? But I have really high hopes that in the next couple of years, with O4 data and DR4 data coming around, we will solve this question. Okay.
All right, so I'll talk a little bit more about part 3 of the open, of the binary and really just stellar physics renaissance, which is in the last decade and a half or so, we've seen really the advent of open source modeling. So codes and tools that are no longer kept behind a single group in a single part of the world, or a few groups shared amongst a few parts of the world, but really kind of distributed user bases, distributed software, distributed code, and distributed developer teams. And so for the work we've talked about, there's kind of three main types of modeling that we've mentioned, going from sort of 3D radiation plus other physics plus hydrodynamic simulations, down to stellar evolution. If you assume the star is a sphere, you can trade that high dimensionality for more detailed physics, including nuclear reactions and other things. You have to then think of what prescription you use to approximate the 3D physics in a spherically average sense. And that's with tools like MESA, modules for experiments in stellar astrophysics. And then all the way down to kind of the population scale. If you can approximate the evolution of a star, then you can sample a bunch of these stars and a bunch of these populations. And so I'll talk just a little bit about each of those kind of three techniques. And the first is 3D hydrocodes with, like the code Arepo, which is a moving mesh code. Here I'm showing the grid. You set up some points. You do what's called a Voronoi tessellation. You let each of these points move with the flow. You ask what is the boundary between each of the 2 points that is close, equally spaced between the 2 points. And then you evolve those with the flow. That's one technique for modeling hydrodynamics. There are codes like Arepo and a whole bunch of others that do this. There's Athena++, which is more of a grid-based code. These are kind of two of the main techniques. There are lots of ways you can solve the hydro, or fluid equations coupled with magnetic fields, radiation, et cetera, on the computer. Athena++ in particular I've used a lot because it has an implicit module for radiation that allows you to couple this radiation transport with both the energy equation and momentum equation essential to solving problems in these very, very luminous stellar envelope where pressure from the photons actually imparts itself on the gas dynamics. Here's just a movie example of this. We see pretty clearly there's 3D things like convection going on. There's pulsations. Here's the density on the left, and then the radial velocity on the right. Not all stars are spheres, and definitely not this one. But stars can be approximated as spheres in order, here, there's an inner boundary cutoff, right? There's, a limited grid domain, limited resolution. We can say, oh, well, if we're doing limited resolution anyway, well, let's simulate the whole star. So this is where tools like MESA come in. This is modules for experiments in stellar astrophysics. Here is a movie of a star. You can see now the radius is being plotted on the left panels. The mass is being plotted on the right. Different patterns correspond to different types of mixing in the star, and then the different colors correspond to, on the left is the temperature of the star, on the right is what is the energy generation happening. And so MESA solves the stellar structure equations, including things like opacities, nuclear reactions, all of that uncertain physics that we mentioned earlier. And MESA itself has been a hugely successful project. It was named as one of the decadal's two impactful open source codes in astronomy. It's kind of the second most used and cited code in single code in astrophysics, just behind AstroPi. Need to breathe. And it has kind of. I was a little mad. I took the screen grab just before. Well. As of like yesterday or 2 days ago, it was at 1, 2, 3, 4, 7 citations. And the larger science community uses this too. So of the thousands of articles that cite MESA, this has generated kind of hundreds of thousands of citations total. And this is not the only metric for a successful tool, but it is one that the community uses often. So it's kind of worth thinking about. Now, and this takes, by the way, to model a star from birth to death, instead of months on a supercomputer, this takes hours on a good desktop, depending on what you're trying to do to the star. It can take days. Now, this brings us to rapid binary population synthesis, which is, okay, it's still a day for one star is kind of a lot if you're trying to draw hundreds of thousands to millions of these and sample a population, so you can make further analytic approximations for this stellar evolution, put that in a code. You have sort of combining single star evolution with some pieces of binary stellar physics, and then you create these binary rapid population synthesis codes that can, in a matter of hours, then simulate a whole population of these things, right? And that can give you now what are the actual rates of different channels for different formation of compact objects, or different types of star populations, or different populations of supernovae, stripped versus unstripped, things like that. And as Lieke knows very well, compact objects and other types of remnants. And so there are a whole bunch of these codes, many of which now are becoming open source themselves. A lot of these are, and there are even, there are some that start with very analytic approximations, others that use tracks from stellar evolution codes that they then interpolate over, and now we're even trying to couple, the community, I should say, is trying to couple more detailed stellar evolution with this binary population synthesis to kind of bridge all of these scales. And similarly, people are implementing 3D findings into 1D stellar evolution codes, et cetera. Okay, so we've talked a lot about a lot of things. Some of this feels very basic to probably many of us. Some of these are a lot of terms we haven't heard before. I think we are probably, straddling both ends of this cartoon of, assuming too much and average familiarity versus also talking to an audience where a lot of people share the same familiarity. So we want to end mostly with some questions, and also, give enough time for your questions, both, what does GRB mean type questions, and also, physics questions. So.
Yeah, and this is actually also a little bit of a segue into the discussion that we'll have after the next two talks. And so I want everyone to grab their phone or actually grab their laptop. And because during the discussion in a little bit, we're going to use a slide deck. We're going to try something that has been very successful during some of the other workshops that have been held at the CCA. And so, okay, if you open it on your phone, you'll have the slides on your phone. But what we want is not to be talking through the whole discussion. We want to have your questions, your input, and your, I actually use stars in my simulations, or, I think actually my simulations depend on questions of how these stars form supernova, or how these stars end their lives, or maybe binary interactions, et cetera, et cetera. And so during the break, we would love if everyone could have a look, open the slides on your computer or wherever, and see the template slides that we put in there, and add your own question, add your own problem, add your own thing. And it doesn't have to be super closely related to anything that we've been saying. We just want to have an open discussion. So with that,
you can also go to tiny.cc/starsandco.
Yes.
And that's a shortened link that brings you to the same slide deck. So tiny.cc/starsandco.
And with that, we take questions, I think. Thank you.
Yeah, thanks so much for a great talk. Questions? Yeah, we have time. I saw Kara first.
Great. Okay. You guys mentioned right in the beginning of the talk that there were these two codes that you were looking at, and they were giving slightly different results depending on which code you're using. I maybe just missed if you guys mentioned if that's resolved, why they're giving different answers, and which one we should trust, or is this still open question?
So I think the answer is mostly resolved in the sense that if you vary things like how efficient you assume your convection is, how you treat the boundary between a radiative zone and a convection zone, how you do your surface atmosphere boundary condition, all of those have much bigger uncertainties and impacts on the core than the differences in certain numerical treatments. So people have done some kinds of code comparisons. I think the answer is actually that observations are needed to help us constrain this. Some of it is better input from 3D modeling on how does material get entrained at a convective boundary is needed. I think both of these codes are wrong in many ways. Some of them are useful. I can give you some systematics. So for example, Kepler does not have any treatment of the overshooting of a convective boundary with convective sort of motion kind of entraining some more material, whereas Franck does not have accelerations, and so it is sort of assuming hydrostatic equilibrium. Depending on which of those you think is a bigger problem, then one of those is going to be preferred or not. I would say that Franck these days has been a bit more reliable, and people are working on it more actively than Kepler. So by the newness criterion, maybe Franck is preferred these days, but again, that's only insofar as some of their approximations are better. MESA would give you a different answer.
Yeah.
And both of these are now closed source codes that, I can't exactly tell you exactly everything that's going on in these because I don't have access to the source code, whereas I have made a similar diagram in MESA. It looks, qualitatively similar to any of these, but exactly where the gaps are,
Let me add a very little note that,
Yeah.
so like 10 years ago, we were at the phase where nothing exploded, right? Or maybe a little bit more like nothing could explode, and we're like, well, we see supernovas, but nothing explodes. Now, some of these models, if you go to the top line, everything explodes. There's been some recent models also that show maybe even a 40 solar mass star still explodes.
Yep.
So we're probably somewhere in the middle, and we're converging somewhat with codes, but there's still a long way to go.
Yeah. Oh, I'll let you.
Yeah, I think I saw it.
Right.
Here's a question next to that.
So you had showed that there's like a relationship between the size of the stars and the probability that they are in binaries. Is there any sense about, oh, yeah, right there. Is there any sense about why this is happening, like a theoretical cause for it?
Oh yeah, on the stellar formation side, I think it has to do with the fragmentation. I'm not a stellar formation theorist, so I don't know exactly. And these are all observational results, right? So this is just taking observations, correcting for the bias that we do not see every binary out there. And we very often miss binaries, unresolved or other ways. This is just saying, okay, observationally, we know that this is why that is. With the star formation itself, I think it has to do with if you have more massive stars, they fragment more easily and you can get a binary. But I don't think that this is a solved problem either.
I've sort of heard it explained, again, also a stellar, stars and, life and death person, not a birth and life person. But I've heard it explained to me as kind of you have more mass and more angular momentum in general in the system. And so angular momentum likes forming something that does this slightly more than, if you just have less mass, then it can be easier to do more of a collapse into one object just because there's less going on. More mass begets more mass in some sense. That's how it's been explained to me, but I think the verdict is still out.
We have time for a couple more. Yeah?
Go back to the alpha versus progenitor mass plot. Yeah, so my question maybe is more for you, but it's for both of you. What path do you see forward to actually sort out whether or not there's a black hole mass gap, first of all? But then, importantly, what the actual microphysics is that explains that. So I see that there's this alpha parameter, which is telling me what fraction of energy give to the stellar material during the explosion.
Pretty much.
I'm not seeing any appeal to actually the interactions or neutrino propagation formula or anything like that in this.
Right. So actually, I can give a little more detail about what this alpha is. So if you assume, like you do stellar convection or other things, that there is characteristic length scale for transport. That is some fraction of the pressure scale height in the material. This alpha is sort of a multiplier on that pressure scale height that is basically an efficiency parameter of convection. This is now neutrino-powered convection. I think that there's a couple directions forward then. One is in the stellar modeling, make more detailed stellar models that better approximate the 3D physics and so on and so forth. There's the other path, which is people are directly simulating this neutrino-powered explosion mechanism, simulating that neutrino convection, doing calibrations, both, either to observations, which is I think what some of these are calibrated to, like 87A, which was the most recent, nearest, biased core collapse where you even saw neutrinos. But there are 3D simulations that actually do solve the neutrino transport directly. When I was saying like now 3D, these are 1D parameterizations of that, when I was saying 3D stars now explode in this movie, that's because people are doing that transport in more detail and doing more refined calibrations of these types of parameters or more detailed parameterizations of it. So this mixing length theory was kind of, version of this explosion engine was born a little bit out of desire to match 3D simulations by one group. And again, these are core and
on the neutron star black hole mass particularly. I think what needs to be done is the moments after the explosion, because what is the theory? Let me phrase this: neutron star black hole mass was an observed thing. People saw there might be a statistical dearth. Then the theory tried to match the observations by saying, okay, well, if you have an explosion, successful explosion, you blow up everything above a neutron star core, you have a neutron star mass left. If you do not explode, you keep that core, you add another extra bunch of masses. But what's really important is what happens after the explosion or after the successful explosion. You might get fallback, accretion onto the star, accretion onto the neutron star at late phases, and you can get any kinds of black hole. So resolving this post-explosion phase, which is at the moment the best of these 3D codes can still only do seconds after the explosion. That is really the theoretical way to solve this neutron star black hole mass gap. But I think observations will solve it before the simulations will.
I have more thoughts on for the sake of. Is there time for that?
There was another question
I think.
in the back.
Yeah. Let's just go for it. Yeah. Let's go.
In the back?
On it. So is it like a prediction with the current data or with the O4 data? And also the peaks that are there, I guess maybe those are the features of the two different mass gaps, but can, with the new data, this become smooth, or that's already impossible?
So you were asking about this one, right?
Yeah.
Not about the how many systems we have.
No.
Yeah. Okay. If you look at the real data underneath this, it's a much more complicated data. This is why I only put a cartoon, and which model you use to infer these peaks will determine what peaks you see. At the moment, we have 90 or so systems, and so we cannot say much more except for 2 of these features are very definitely confirmed, and that is this 35 solar mass peak. It will not leave. There's no way. It has been confirmed in like 20 different ways, and it's been studied to death. And this 9 solar mass peak is slightly less certain. I do think it is where the global overdensity, the global peak of the binary black holes is. But what is a little bit uncertain is as you go to lower and lower masses, your systems are less and less loud, and you can see less of them. So we have less and less systems as we go down. And so whether or not there really is a dip below here, or if that just has a kind of smooth going up all the way to binary neutron stars is uncertain. I think it's going to be a very low dip, maybe, but this is guesses. But I think O4A is already going to double the number of systems, and so in here we have of the order of I think 20 systems. Maybe Umberto will know better. 20 systems, so we'll go to 40 systems. So that's already a good increase in statistical noise. And here the same, we'll go from like 30 or 40 systems in there to like 80 systems just in that peak. So those 2 are not going to disappear. There's a lot of debate on additional structure. There's a debate on whether or not it dips down here, whether or not there's an extra feature in here, and whether or not this is going down or not. These are all questions that I think in the next 3 releases, we'll have a really good chance of answering those. In particular, I am very hopeful that we'll find what is probably the real edge of parent stability supernova. And I am also very hopeful that we will be able to say how deep this dearth is, if there's any dearth at all. But Wednesday, maybe.